This is just like a rocket.
This is the Sanford Street School in Glens Falls, New York. These fourth graders are flying rockets they have built themselves. The scene is not an unusual one. It is, in fact, rather typical. What may seem unusual about these 8- and 9-year-olds is that they understand.
What makes a rocket go?
The classroom experiences you are about to see were recorded as they happened on location at the Sanford Street School. The classroom teacher is Miss Elizabeth Houghton. Her students spend an average of 2 hours a week in the science program. Observing Miss Houghton's class as a student teacher is Miss Suzanne Daly, a senior at the State University College at Plattsburgh, New York.
My cartridge is really cold.
I wonder what makes it cold.
I don't know. Ever since I turned it off, I've been wondering.
What do you suppose is inside of it?
Well, I read on the package there's carbon dioxide and some other things in it.
We'll have to put that on our list of problems and find out why it becomes cold when we puncture it, won't we?
Yeah.
The children drew a flight line on the blackboard based on their own arithmetical scales. As one part of a full fourth grade curriculum, the science program draws upon and further develops the skills of arithmetic, social sciences, and the language arts. Through a series of evaluation lessons, we will review the highlights of 6 weeks of the science course.
Miss Houghton, when will we start work on our new list of problems?
That's a good question, Mark. But if I remember, some people last week told me that they had some things they wanted to show and tell Miss Daly this week. Remember the plans we made?
Yeah.
I think we should do that first, don't you?
Yeah.
Let's go back and look at our list of original problems. Julie, would you read them, please?
A. What makes a rocket fly? B. How can it fly without wings? C. Why is there no propeller on a rocket?
Everyone read D.
Is a rocket like a jet plane?
You read E, Julie.
E. Does a rocket push on the ground when it blasts off?
Did we think these were good questions when we made them?
We thought they were when we made them.
Why did we change them?
When we looked for the meaning of the word fly in the dictionary said the word fly most often means to move through the air on wings. Rockets don't have wings and can move through other things besides air.
Did we make any other changes?
We thought a rocket pushed on the ground when it blasted off. After it got going, we thought it pushed on the air.
Peter, will you tell us again?
After it got going, we thought it pushed on the air.
John?
Then we found out the push was on the inside of the rocket and nothing outside of it.
What one thing does A, B, C, D, E ask? Anyone?
What makes a rocket go?
Find any answers to that problem?
Yeah.
Where do we find our answers? Joel?
I found some books at home.
Judy?
Yes, I have some science books.
Did you find anything?
Yes.
John?
I thought up my experiment.
That's good. Marcia?
Miss Houghton, may we show Miss Daly what we did with our balloons?
I think that'd be fun.
Miss Daly, would you like to push the balloon?
Thank you. Nancy, we did?
Yeah.
The free-flying balloons were their first rockets. But since the flight of balloons was so unpredictable, the class quickly began a series of experiments designed to overcome a basic problem. How can you control the air rushing out of a balloon? A simple and effective means was provided by the top of a common plastic squeeze bottle. Like many of the children, Deborah Barton found this useful tool in her mother's kitchen. Debbie's idea helped to solve the problem of air release, while at the same time, her experiment added the word friction to the class vocabulary list. To help overcome the friction of the floor, a major alteration was necessary.
Well, I think that one's making quite a trip, don't you?
Yes.
How many times is that?
This will be the 6th one it's there.
Almost 8. Certainly went farther than Julie's, didn't it? How about you, Peter? What have you got there?
Well, this is a rocket boat. I blow up the balloon and put it in the water and see what happens.
Well, that was almost like a motorboat, wasn't it?
Yes.
And John, what have you?
I have a toy tank here, and this is called a rocket tank. I tied the neck of the balloon onto the tank with a string. I'm going to blow it up and see what happens.
Cellophane food bags and paper clips comprised one of their first guidance control systems. The experiments were gradually becoming more refined and complex, and along with progress, an occasional setback.
Is it going to go all over like Judy's did?
No.
Dear.
Gee, it didn't work.
Soda straws on the flight line improved speed and control. The nylon fishing line worked far better as a flight line than did ordinary string.
What are you going to do, Rhonda?
I'm going to cut a hole in the end of this balloon, like this. Now, I'm going to twist the end of the balloon. I'll blow it up now.
Got it?
Will you tie this, Joe?
Yes.
Thank you. Nancy, will you put the tape on?
Why did you cut the hole in the balloon?
Well, to make a slower reaction.
Slower? You going to let it go now?
Yes.
Good. It was much slower, wasn't it?
Yes. George, Snap, and Billy are down at the bottom. Nancy, Clausen, and I are at the top. Billy has his foot under the flight line. George Knapp is a straw through the flight line. He is taping a balloon onto the straw. I am holding the flight line up at the top. Are you ready, George? Okay. ready, George? 5, 4, 3, 2, 1, 0. It almost hit Mark in the face. It did.
Have you released your balloons in enough different ways and enough different times to always predict what is going to happen?
Yes.
Judy?
I'm satisfied we did.
Peter?
The balloons always run in one direction and the air in the other direction.
Have you thought about the reasons for this?
I found something in a science book that I think is good. I found something too.
John, would you like to tell us what you learned from your book?
I learned that another way to show how a rocket goes is by using a toy balloon. Now, Joe, would you please come up here with your balloon? All right, now Joe's balloon here is like my chart up here. Now, when he blew up his balloon, he pushed in air molecules so they would be close together and pressing against each side with the same amount of force. All right, Joe, would you squeeze your balloon? All right, now when Joe squeezed his balloon, he pressed the air molecules closer together so they would be trying to get out with much more force. Now, release your hold on your balloon. When he did that, the air molecules floated apart or moved apart, and the balloon went back into its normal shape.
May I have everybody's attention? Are you ready, Scott? Let's look at number 1, Ellen. Number 1 says, what is the meaning of law as used in Newton's laws of motion? Could law have more than one meaning, do you think? Could it mean things as well as people? I'd like to have some people look up the meaning of the word law this week as used in Newton's third law of motion. Are there some of them who would like to help Ellen? Let's look at number 2. What other scientific knowledge did Sir Isaac Newton give to the world? How old was he when he began his first scientific experiments? Here we have a record about Sir Isaac Newton. I think perhaps if you play this record, you may learn some things about some of the other scientific inventions or knowledge that he did give to the world. Are there some people that would like to work on this? Also, I think we'd like to find out how old he was when he first started. Number 3. Let's look at number 3. What illustrations can you find in the film strip library that help you to understand Newton's third law of motion? Remember back when we looked at some of these space films? I think some people would like to go back again and see if they can find some illustrations of Newton's third law of motion. Let's read Mark. Third law of motion. To every action there is always an equal and opposite reaction. Now I should like to have you look at number 4, because this is something that everyone is going to do. Be prepared to show an application of Newton's third law of motion. What do I mean by the word application?
That's like an application to join the YMCA.
That could be one meaning of it, George, but it would be the meaning in this one?
No.
What would you think would be the meaning?
I think it could be an experiment. Or a report.
Next week, I'd like to have every single person do something about number 4. Bring in many different things that would apply to Newton's third law of motion. Other things besides balloons. If you need any help, you may come to me during your science work period this week, and I'll try to help you find the things that you need. And then besides number 4, everyone is going, I want to see how many people can do that, have something for number 4. How many think they can? Oh, I know you can. Besides number 4, I'd like to have you choose one of the other 3.
Several days later, the children discussed the results of the homework assignment. The word law, while not new to the class, had a new meaning as far as their science project was concerned. Now it became a statement of something which, under given conditions, happens over and over again. Chris Brummett listened to the long-playing record and reported that Newton wrote laws about gravity as well as about motion. The class was surprised to learn that Isaac Newton wasn't much older than they when he began to think about gravity and motion, and that he wrote his laws when he was just 23 years old. The young scientist could hardly resemble a white-whiskered old patriarch often pictured in science books. One of the homework essays was about Newton's school days. His teachers, it was reported, did not consider the young Isaac to be especially bright. What was even more unbelievable, according to the report, was the fact that they recommended no further schooling for Newton on the grounds that he was a very poor student.
Now, are we ready to show that Newton's law of motion will work with many different things, not just balloons?
Yes. Well, when Peter went backwards, the skates went forward, and the action was when Peter and I went forward, and the reaction of the skates, and the reaction is the movement of the skates. And now Billy is going to stand on the skates and just step up. When Billy stepped off the skates, there was a smaller action and reaction. The larger the jump, the larger the action and reaction.
My father told me about how a gun recoils. The reaction of the gun is called the recoil. Now, when I pull the trigger like this, the gun is going to go backwards, like that. You see, when the firing pin hits the bullet goes off in one way, which is the action, and the force in which the bullet pushes the force in which the gunpowder pushes the bullet down through the barrel is the action, and the reaction is when the gun goes backwards.
Real good.
When the water boils and the steam are collected in the test tube, the steam got so in around there, it blew off the cork. The cork blowing off and the steam boiling and the water boiling was the action, and the test tube going in the opposite direction was called the reaction. That is how a gun recoils.
The steam is going to come out these nozzles. Watch for the steam coming out the nozzles and the steam engine turning around.
It's hard to see the steam even though it's coming out, isn't it?
Yes.
We know it's coming out because what?
The steam engine is turning around, so that means the steam is coming out the nozzles.
And where is your action?
The action is the steam coming out the nozzles, and the reaction is the engine turning around.
In true scientific fashion, there were numerous variations demonstrated over and over again. There was a free exchange of props and ideas, and many original uses of familiar objects.
Who tried to show that for every action there was an equal reaction? Diane?
I think Joel did with the roller skates. He showed that when he jumped farther, he made a bigger reaction and an action. And when he made a smaller jump, he had a smaller action and reaction.
We need to find out if we know the answer to our one main problem. What makes a rocket go? I think the best way to do this, and to the answer the questions under it would be for us to write a report with the title, What Makes the Rocket Go? You might use this as your outline and try and include in your report all the answers to these questions. How well you do this report will tell both you and me if we've answered our problem. What makes the rocket go?
I've got my rocket done. Are we going to test them outside next Monday?
Thank you for reminding me, Scott. That would give every one of us a chance to finish our rocket. How many people have theirs finished now? The others, as soon as you finish your rocket, you may bring them to me and get one of these cartridges. Be sure and wedge them in very tightly, like I showed you the other day.
The outdoor rockets are powered by an ordinary carbon dioxide cartridge of the type available in hobby shops and drugstores.
These were excellent reports and show that you did a good deal of thinking, and I'm sure that you've solved the answer to all the questions to the problem, what makes a rocket go? We'll have time for only a few of them. The rest I'll put on the bulletin board, and you can read them when you have time. Julie, would you like to start?
What makes a rocket go? Rockets do go through the air when they blast off, but out in space where there is no air, wings are of no use. Airplanes and jets need wings for balancing, steering, and other things too. Without wings, jets and airplanes could not fly.
Jets will not work in space, but a rocket will, because a rocket needs no air, and a jet does. Rockets, too, need oxygen because they carry their own in solid or liquid fuel. In a liquid fuel rocket, tanks of liquid oxygen are pumped into the combustion chamber, where they are ignited.
The rocket has the simplest kind of engine because it has only two main parts. A simple rocket engine has no moving parts. The first part is the tube. The second part is the nozzle. If it is difficult for you to imagine a gas in some different form, think of the fact that steam, a gas, comes from water, a liquid, which in turn can become ice, a solid. All three are the same substance at different temperatures. In an actual rocket, fuel and liquid oxygen burn fiercely when they combine. The heat caused by combustion greatly expands these liquids so that like water turning to steam, they become a gas. The expansion takes place very rapidly and builds great pressure. Since there is a nozzle at the rear, the gas shoots out and the rocket shoots ahead.
A rocket goes because of the kick inside of the rocket. A rocket has to go at a very fast speed to overcome the Earth's gravitation.
Mark has something to show us.
What I have here is a Coke bottle, baking soda, and water, and vinegar. I have 5 pencils, and they are spread on the desk about an inch away. I am going to put the vinegar in.
Just a moment, Mark. You told us that your experiment was something like John's. How is yours different?
Well, instead of using water and making steam, I used soda, vinegar, and water. Well, I'm going to put the vinegar in.
What's your problem, Mark?
Well, it just works so fast that I can't get it down on pencils.
If you can tell us what your problem is, Mark, perhaps we could help you.
Well, the chemicals mix so fast that I can't get the cork on.
What do you want to do to the chemicals?
Keep them apart so I have time to put on the cork.
Perhaps there would be some other kitchen chemicals that we could work on that would slow down the action. Is there anyone else that would like to work on this? Help Mark out? Chris told me that he had a problem, too.
I've been thinking about a rocket way out thousands of miles in space, out where there is no air. I've been thinking, too, how a rocket would leave the moon. Scientists say there is no air on the moon. I'd like to be able to take the air out of something so it would be like outer space and like the moon.
Can you state that in a problem, Chris?
How can we take the air out of something so it would be practically a vacuum?
Ellen, will you write down Chris' problem and Mark's problem that he wants to slow down the action so he can get the torque on?
The work of these fourth graders traces a familiar pattern of scientific research. The resolution of the original problem, what makes a rocket go, now appears to be merely the beginning. Natural curiosity, initiative, and imagination have led to a new set of problems, a new class project. The technological hardware is as elaborate as balloons, milk cartons, and roller skates. Their resources are as far away as the school library and the houses they live in. The children of Glens Falls, New York are just like children in every American city and town. This has been a story of the teaching of elementary science in the space age. The project was conceived by Irene C. Potter, Elementary Science Coordinator, Glens Falls, New York, and June E. Lewis, Professor of Science and Science Education, State University College, Plattsburgh, New York. The producers of this program wish to acknowledge the cooperation of the Glens Falls Board of Education, Glens Falls, New York. For additional information on the teaching of elementary space science, write to National Aeronautics and Space Administration, code AFEE, Washington, D.C.